Hi. I know that that instant search wizard was very appealing to you all. I'm going to talk to you about rotational motion and energy. So, our topic is energy and rotational motion. And again, we're just going to talk about what happens if we have something that rolls, that doesn't just slide. I mean, the key example I think of is this one. We got a ramp and a box, and it slides down the ramp, and so at the very top here, it has energy, and at the bottom it has energy too. And remember we said that E equals E prime. And again, we're assuming that friction is 0. So it just slides down. In this case, GPE plus KE at the top equals GPE plus KE at the bottom. Well, at the bottom, this is 0. This is, oh, sorry. I lied. Okay. This is 0, so we're going to have this equal to that. And we can solve for how fast it's going. No matter how steep this is, as long as the height's the same, we're going to end up with the same speed at the bottom. But what happens if instead we have something that, the same ramp supposedly, but we have something that rolls? Well, first, if there's no friction on here, will it roll? The answer is no. It will just slide along here. And in that case, it's exactly the same as the box example up here. The GPE at the top is going to equal the KE at the bottom if there's no friction. If there's enough friction for it to quote-unquote catch, so that it has a small torque on it, like a small force that applies across the radius. And let's talk about that. If we have a small force, like in other words, small, then when we have gravity acting down on the block, we're going to have a small amount of friction in that direction. And that friction is going to make the wheel start to turn. So we're going to end up with a normal. And we're going to end up with a small rotation along here. So we call that, so in this case, we call that rolling. Well, in all cases, we call it rolling without slipping. And if you notice, when you put the box on there, or you put the circle on top of this, it's not enough friction to keep it from moving. Otherwise, it would be a significant amount of friction. But if it's small enough that it will roll, so it's not high enough to keep it in place, but it's big enough that it won't just slide down the ramp, then you're going to have rolling without slipping. And what that means in our case is that we're going to have kinetic energy of rotation too. So we have to talk a little bit about that. I can spell words. I gotta do that again. All right. Oh, come on. Okay. So the kinetic energy of rotation is what we're talking about. And we said before that for translational, for linear motion, that kinetic energy equals 1/2 mv squared. Well, we're going to say the same thing, except we have our analog to rotation, to mass, is the moment of inertia. And our analog to translational motion is going to be rotational motion. So we're going to say this is going to be angular velocity. So let's see what that looks like. So technically, what we call CROT, kinetic energy of rotation, is going to be 1/2 I omega squared. And then let's see if we need any fudge factors for it. Well, I, the units, are kilogram meter squared. And the units for that are radians per second, which is 1/seconds. Remember, radians is a fake unit. So if we multiply those together, we get kilogram meter squared over second squared. Woo, we win. So it turns out that the expression for translational, I'm going to start calling it translational or catrans. And it turns out that it leads us right to the expression for rotational kinetic energy, or CROT. So so let's take a look at that rolling without slipping thing again. So we have a sphere at the top. Mu equals roll without slip. Okay. I don't even have to know what that is yet. Okay. But I do know that it's going to come down this way. Well, first, one of the things you'll notice is that it will actually have a slower linear velocity than it had before. But we'll take a look at that in a second, because now you're going to use part of the energy that you used to use to come down the hill, or they used to use just for moving down the hill. Well, someone's now going to get used to rotate it. So we're going to have to deal with that a little bit. At the top, we're going to have GPE. We'll call the initial velocity 0 like we've been doing. But at the bottom, it's going to be CROT plus catrans. So it's going to become kinetic energy at the bottom. So this is going to be mgh, just like before, but it's going to be 1/2 m, I omega squared plus 1/2 mv squared. And we're going to figure out ways to combine these two. We're going to have to come up with ways to combine those two. The way we're going to do it is by looking at this term and how we convert it into one of these terms. But that's all right. I mean, we're going to try that out right now. So maybe we will. And there we go. Okay. So if we take a look, all we're going to have then is mgh equals 1/2 I omega squared plus 1/2 mv squared. Now, before we were used to masses canceling out, but mass won't quite cancel out because we have moment of inertia. So let's look at an example that rolls without slipping, and we'll call it, we'll say it is a solid cylinder of mass m, capital M, and it goes from some height h. And we'd like to know at the bottom what is v in terms of our givens. Well, we go back to this relationship. mgh equals 1/2 I omega squared plus 1/2 mv squared. And we're going to have the moment of inertia. This is a solid cylinder. So for us, that means that I is equal to 1/2 m r squared. it also means for us that this omega, we have to relate it to V somehow. Well, we know that V is just R omega, so that means that omega is V over R, and we're going to find we make this substitution all the time to combine those two together. So we have mgh equals 1/2 capital M R squared. We should give this a radius R. We'll even capitalize it for fun. Okay. Plus 1/2 capital M V squared. Oh, I didn't put omega squared in there either. Okay. Well, let's simplify a little. mgh equals 1/4 mr squared omega squared plus 1/2 mv squared. By the way, we should go back here actually, and we should go back here and this capital M. See, I figured out how to erase again. Well, good times. And that means the masses are all going to go away. Everybody loves that. Now we're going to do our magic with omega. So we'll have GH equals 1/4 R squared V squared over R plus 1/2 V squared. So these two, actually it's V over R, quantity squared, sorry. So we're going to end up squaring these. So we have 1/4 R squared V squared over R squared. Ooh, gotta love when that happens. Okay. Plus 1/2 V squared. Those go away. We have 1/4 V squared plus 1/2 V squared. That'll be 3/4 V squared. And GH. So V is going to be square root of 4GH over 3. Now, I want to compare that to what we get if it just slid down the hill. If it just slid down the hill, remember we'd have 1 mgh, we'd have the GPE at the top, equals KE trans at the bottom. So we'd have that equals 1/2 mv squared. Those divide away. 2GH square root equals V. I just multiplied by 2, took the square root. I want to point out that, like I said, this is slower. This is considerably slower. Instead of root 2, we're going to have root 0.33 or 1.33 or whatever 4/3 is, which is 1.33. Woo! So, and my point is that if you notice that this rotational thing makes it go a little bit slower. Now that's not a loss due to friction, because the friction that's there is really, really small. Otherwise, it would take a lot of work out of the system. But it's not. It's enough to make it slip, or to make it roll, but not enough to actually make it go. So, we can talk about all kinds of examples like this. You know, we've done a problem with what is that stuff called? We've done problems with pulleys with no mass. Well, all of a sudden now we've got another element that has some form of rotational energy in it. So before we would have said that if we have a table, again, my famous Stonehenge table with this thing here, we have a block, it goes over here, that the energy that started out in the system was GPE. From this, we'll make this mu equals 0. And we would have said that it equals the KE at the bottom of both. So if I call this big M and little m, this would be mgh, if that's how far it's going to fall. That's when it stops. Equals 1/2 m plus m v squared, which works terrifically as long as this pulley is light and frictionless. That's why they use those magic words. If you look, the energy would change here. The GPE would certainly be here, but this wheel is now going to spin. So now, if the pulley is not light and frictionless, I can write words. I have an eraser thingy. And frictionless. Now the GPE is going to equal KE trans for both plus KE rotational for the wheel. So it'll be something like mgh equals 1/2 little m plus big M v squared plus 1/2 I of the wheel omega squared, which again you'd have to replace with v over r and all that good stuff. So you can see it gets more complicated. It also means, by the way, that it's going to go down a lot more slowly. It's going to be a more difficult problem to solve in some ways. And we're going to talk more about that later. But those are the main, the principles that we're looking for energy in rotational motion. I will try to, well, I won't try. I will put a PDF of these notes in the shared drive if you need them. Thanks for watching.